Okay, hey guys. Okay, so I'm going to talk a little about the applications of dynamic equilibrium in industry, because industry is one of the biggest reasons why we as chemists want to understand how reactions occur and how they work. We particularly as teachers will be teaching kids who will hopefully in the future become the people who develop or maintain processes in medicine industry, where the goal is to get the products you want of a high percentage yield with high atom economy in the most cost effective and safe way. So the Haber process is probably badly spelt. The Haber process is probably the most important one at GCSE because all of the examining boards cover it. So we need to make sure that we as teachers understand this one inside out so we can pass on all the information. So if we look at the equation, nitrogen plus hydrogen becomes ammonia. And this is an exothermic reaction. Okay, so as I said, the reaction is exothermic, which as Sasha and Rahim have explained, means that if you increase the temperature, following Le Chatelier's principle, the reaction will go to the left, and so it decreases the yield of ammonia. If we decrease the temperature, again, following Le Chatelier's principle, reaction goes to the right, which means we increase the yield of ammonia. So if you just consider the dynamic equilibrium, we would think that the temperature should be kept as low as possible to ensure a high yield. But the temperature that is actually used in the manufacture of ammonia is 400 to 450 degrees C, which means a very low yield, only 15% in fact, which sounds really unimpressive given that the cost of producing a temperature like that would be quite high. But the important factor here is not how much yield you get, it's how fast we get there. So if you do have a low enough temperature to get 100% yield, it'll take several years to get to the dynamic equilibrium to get that yield, which is neither cost effective or efficient. So 450 degrees is a compromise temperature. Now, if we go back to reaction rates and we look at a Maxwell-Boltzmann curve, so number of particles, energy. So if this is our curve, if we increase the temperature, we do two things. So you increase the kinetic energy of all the molecules involved in the reaction, so you get a higher number of collisions per second, but it also leads to all the molecules having a higher, generally higher energy, which means that more will have energy above the activation energy. So by increasing the temperature, you will get a higher rate of molecules colliding with sufficient energy. Don't forget, you do have to break those bonds in your nitrogen and your hydrogen. So the Haber process does happen very quickly, even though the yield is low. But it's not a problem because what happens is the mixture is cooled, and so once it reaches dynamic equilibrium, the mixture is cooled, and the ammonia has a higher boiling point, so it condenses first, gets removed, and you're left with nitrogen and hydrogen, which then is recycled back and reused in the reaction. So if we look at another reaction, this one is an endothermic reaction, and it's a slight cheat because there are no dynamic equilibrium reactions, well, not ones that I could find anyway, studied at GCSE or A-level by any of the boards that have an endothermic reaction. So this is the production of lime. So the production of lime isn't actually studied as a reaction in industry or anything, but all GCSE students should have come across it because it's the decomposition of limestone. Okay, so you've got your limestone, which becomes calcium oxide and carbon dioxide gas, and this is a endothermic reaction. One. Okay, it's a heterogeneous reaction because you have a solid on this side and you have solid and gas on this side. So because it's endothermic, if you add heat, your forward reaction is favoured. And if you add heat, also the rate of reaction increases. So it's a win-win. So if you increase the temperature, you get high yield, and you get a high rate. Okay, in industry, they can use 900 degrees C, but some places will use 1000 degrees C because that increase in rate, the reaction is worth the extra cost in maintaining the heat. Okay. As I said, this is a cheat because students won't study lime production as an important industrial process, but at Excel, AQA will do the blast furnace, which, if you remember, is the extraction of iron. Yes. Okay. And in the blast furnace, limestone is added, and the temperature in the blast furnace goes anywhere from 400 degrees C to 1800 degrees C. So at this temperature, the forward reaction is favoured, so you get all product, so you get all lime, calcium oxide, which is used in the blast furnace to decompose, which is used to neutralise the acidic impurities from the iron ore.